This is Physics 156, and we're in Chapter 6 doing problems. This problem is number 4. We find that we have a 1,200 Newton cart, and it's on a floor. So there's a cart, there's the floor. How much work is required to move it at a constant speed for 5 meters? Well, force, work is force over a distance. So 1,200 times 5 would be 6,000 joules. I guess I should read the whole problem. That would be a good idea. There's also force of friction, and the force of friction is 230 newtons. So I gotta move. The work is against that force of friction, because I'm not coming against gravity. 230 newtons times 5 meters, and so I'm talking about 1,150 joules would be required to do that. And if I were to go vertically, so that's part A. Part B, work vertically, lifting it off the floor, would be the entire weight times 5. So that would be 6,000 joules required of work to lift it 5 meters vertically. Number 7, a certain library shelf is 15 centimeters off the ground, and the remaining 4 shelves are each 38 centimeters above that one. Okay, so I got them above the ground, 15 centimeters, and then I got another shelf 38 centimeters above that, and the remaining 4 shelves, 1, 2, 3, 4. So there's 38 centimeters there, 38 centimeters there, 38 centimeters there. Okay, that blah blah blah. If the average book has a mass, so book mass, um, 1.4 kilograms. Now we want the weight of the book, so the weight of the book would be 1.4 kilograms times 9.8 meters per second squared. And so we'll use our calculator to get that number. 1.4 times 9.8, 13.7 newtons, 13.72 newtons. All right, so the issue is, if the average book has a mass of that, with a height of that, okay, so I got 22 centimeters as the height of my book. And on average, the bookshelf holds 28 books. I got 28 books per shelf. How much work is required to fill the shelves, assuming the book are all laying flat on the floor when you start? Flat? Okay, so here's my bookshelf, and my books are arranged around it flat, so that if I do work going this way, work going that way cancels each other out. So I have no horizontal work happening. All my work is just vertical work. All right, now the issue is, where am I holding the book?
In the middle.
And so if I hold the book in the middle, then that's going to be at 11 centimeters. All right, so we're going to do summation 1 through 28 for the 8 books, and we're going to go times 15 centimeters plus 11 centimeters times the weight of each book, 13.72 newtons. Okay, so that'd be the first shelf, and then we would go plus summation 1 to 28, 15 centimeters plus 38 centimeters plus 11 centimeters times 13.72 newtons. And then we go plus summation 1 through 28, 15 centimeters plus 38 centimeters plus another 38 centimeters plus the 11 centimeters that I'm holding the book up by times 13.72. And then I do it, so that's first shelf, second shelf, third shelf, 1 to 28, 1 to 28, the height times 13.72, 13.72.
So would you just keep adding the 38 centimeters for each shelf?
Yeah. So I'm going to go 15 plus 11 is 26 centimeters. And of course I want to change that to meters. So 26 plus 38 gives me 64 centimeters plus another 38 gives me 102 plus another 38 gives me 140 plus another 38 gives me 178. Now we want these guys to be in meters, so we're going to put a decimal point there, call it meters. Decimal point there, call it meters. Decimal point here, call it meters. Decimal point there, call it meters. Decimal point there, call it meters. Okay, so now we're ready, and so I got 28 of them, so I'm going to go 28 times 0.26 times 13.72 plus 28 times 0.64 times 13.72 plus, I'm down to the third one, 28 times 1.02 times 13.72. Okay, now I'm going down to the next one, plus 1.4 times 28 times 13.72. And then I'm going to go down to the last one, 2 times 1.78 times 13.272, and I end up with a total of 1.3 kilojoules to the 2 significant digits that I have, because I only have 2 significant digits in the problem. Oh, bummer, I got 3 significant digits. All right. Put a 2 there. Okay. That is 7. Moving on to 18. How much work must be done to stop a 925 kilograms car moving 95 miles per hour. Now we need to change miles per hour. Is it really miles per hour? No, kilograms. Kilometers per hour. We change kilometers to hour to meters per second. We divide by 3.6, and we get meters per second. You do know why that is, right?
Because it's science.
All right, so we'll go through that. 26.39. All right, so I got kilometers per hour, and I want meters per second. Okay, so there's, in 1 hour, there is 60 minutes. In 1 minute, there is 60 seconds. And in 1,000 meters, there is 1 kilometer. So this is 1,000 divided by 3,600, which implies that if I divide by 3.6, I'm going to end up with meters per second. So we remember the 3.6 and use it often. The other guy that we remember is when we have revolutions per minute and we want radians per second, we multiply by pi over 30. That's the only one we remember. So those two conversions we remember and use often. Anyway, back to the problem. I have a certain amount of kinetic energy, 1/2 mass velocity squared. So 1/2, 925 kilograms, 26.39 meters per second squared. And that's going to be some number of joules. 0.5 times 925 times 26.39 squared equals, so I have 3 significant digits, 322 kilojoules, and if that's the kinetic energy I have, then the amount of work I need to stop the car is the same as its kinetic energy, 322 kilojoules. So the work I have to use to stop the car is the same as the kinetic energy. We're done. And number 21. An arrow of 0.085 kilograms, because we want it to be in kilograms, is fired from a bow with a string that exerts an average force of 105 newtons. The arrow, on an arrow over a distance, the distance is 0.75 meters. What speed does it leave the bow? Okay, so we have some work that's being done, force over a distance, 105 newtons times 0.75 meters. So we have some amount of joule of work that's being done, 150 times 0.75, 78.75 joules. Now that joule is going to be converted into kinetic energy, which is 1/2 m, 1/2 m v squared has to equal that 78.75 joules. All right, so V has to equal square root of 2 times 78.75 joules divided by the mass, which is 0.085 kilograms. So the velocity as I leave the bow is, square root of 2 times 78.75 divided by 0.085, 43, and we only have 2 significant digits, so we'll call it 43 meters per second. Yeah, that was 21. 22 is next. No, 26. Number 26. How much does the gravitational potential energy of a 54 kilogram pole vaulter change if her center of mass raises 0.4 meters above? Okay, so potential energy is mgh. I know the mass, 4.0 meters. I know what gravity, 9.8 meters per second squared. And I know the mass, 54. Well, I got the mass in the distance in the wrong spot, but that's okay. So this is the mass is supposed to be first, and the distance is supposed to be last. But that's beside the point because it's going to be the same number. 4 times 9.8 times 54. And I have how many significant digits? All of 2. So I'm going to call it 2.1 kilojoules, the 2 significant digits. 35 is next. And I guess we got enough paper here to do number 35, so we will. Oh, can I pick a different pretty color? Wow, I can. I can pick a really pretty color. Alright, well, I'll quit doing that. Work the problem instead. Alright, 35. A spring of spring constant 83 newtons per meter hangs vertically next to a ruler. Okay, so here's my ruler, here's my spring hanging vertically. The end of the spring is next to the 15 centimeter mark on the ruler. If I go and hang a mass on it, like that, and the mass is 2.5 kilograms, it is attached to it at the end of the spring and allow the mass to fall. Where will it end up on the ruler when the mass is at its lowest point? Okay, so now the issue is, where's 0? So we'll assume that 0's up here and down here is 100, and that's the way our ruler is. Okay, so I have some potential energy at the spring, of the mass, mgh. Alright, so that's going to be 2.5 kilograms, 9.8 times some height. So I'm gonna move from here to someplace else, and then I have some potential energy caused by the spring, which is going to be 1/2 kx squared. So 1/2 times 83 times x squared is going to equal to 2.5 kilograms, 9.8 meters per second x, because that is the height. Alright, so x could be 0. So that could be, and that would be a perfectly legitimate answer. Everything could be 0, and those two things would be the same. Or 1/2 83x is equal to 2.5 times 9.8, 24.5. X is equal to 24.5 times 2 divided by 83. Something's not right. I'm not sure exactly what it is. Oh, these are meters. Okay, right. This would be in meters. 0.59 meters. So X is going to be 59 centimeters. And then we're going to add the 15 to it because it wants to know where I am on the meter stick. So final answer is going to be 74 centimeters. Okay, what problem was that? That was 35. We'll read it again. Yeah, exactly. That's what I wanted to know. 70. Now, it really doesn't want to, this thing also bounces around. It really didn't want you to comment on bouncing around because that's not this chapter. Number 40, but I think chapter 11 or 12, you end up with the string bouncing up and down. And I have to worry about it then. All right, so I've got this here roller coaster, and it's doing that. And I've got 32 meters there. And I've got 26 meters here. And I've got 14 meters. I guess we only do this twice, and I got 14 meters there. So there's only 2 homes. And this is 0.1, 0.2, 0.3, 0.4. All right, calculate 40. The roller coaster, blah, 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 assuming frictionless. The friction calculation of speed, point, blah, blah, assuming no friction. So I want to know the speed at points 3, 4, and 5, assuming that the velocity at 1 is 0. So I have some potential energy at 1, mgh. 35 times 9.8 meters per second squared times h. All right. When I get to point 2, all of that is kinetic energy. So kinetic energy at point 2 is equal to 1/2 mv squared, which has to equal the total kinetic energy, 35, 9.8 mgh. Again, I put the m's and the g's in the wrong spot, so I hose myself over. So mgh 32. 32? Yeah, 32 meters. And where did we get this 35 from, I wonder? 35 meters. Now, as luck would have it, the mass goes away, so I don't care about it. So velocity at point 2 is going to equal the square root of 2, 9.8, 35. And it's going to be in meters per second. Square root of 2 times 9.8 times 35. And I end up with 26.2 meters per second. All right, now I ask myself, at point 3, so I'm at point 3, okay, and I start off with some potential energy, mgh again, so my potential energy from point 1, and that's going to have to equal my kinetic energy at point 3 plus my potential energy at point 3. All right, so we look at that equation and say m 9.832, m 9.832 is equal to 1/2 mv squared plus m 9.8 and my height is 26. 26. Okay, and we look at that and we say, okay, well, that's fine. Again, my masses go away. I have one in every term, so they can go away. So my velocity is going to equal the square root of 32 minus 26 is 6. So 9.8 times 6 times 2. Square root of 2 times 9.8 times 6, 10.4. 10.4 meters per second at 0.3. Okay, now we're going to do the 0.4 problem. Okay, so I'm looking at 0.4. And I'm saying that my potential energy at 0.1 has to equal my potential energy at 0.4 plus my kinetic energy at 0.4. So M 9.8 32 has to equal M 9.8 14 plus 1/2 mass velocity squared. And I look at that and say, well, I got mass in all the terms, so it can go away. So that is also known as convenient. And I find that V is equal to square root of 2, and 32 minus 14 is 18. Yes, it is. 2, 9.8. 18. Square root of 2 times 9.8 times 18, and I get 18.8. 18.8 meters per second. And then I go back and do an idiot check, and I say, well, the first speed should be the fastest. I have 26.2. This should be the slowest, 10.4, and it is. And then at 0.4, I have 18.8, which is a little bigger than being at the bottom. Okay, well, that worked out just fine. That was number 40. Now we're looking at 47. 47. Okay, I've got a 16 kilogram child. Alright, descends a slide, so I got a slide, and it's 2.2 meters high. Starting from rest, and reaches the bottom at 1.25 meters per second. How much thermal energy does the friction, due to friction, was generated in the process? Okay, so I got some potential energy at the top, mgh, 16 kilograms, 9.8 meters per second squared, times 2.2 meters. 16 times 9.8 times 2.2. 344.96. 344.96 joules. And we can carry that many significant digits because we only apply significant digits to our answer, not to intermediate answers. All right, now the child also has some kinetic energy. 1/2 mass velocity squared. That's a 1. Alright, so 8 times 1.25 squared and that's going to be 12.5 joules. Okay, so the frictional loss will be the potential energy minus the kinetic energy. 344.96 minus 12.5. 332.45 joules, and so that frictional loss will be all due to heat. So for a final answer, this is 47, and we have 3 significant digits, so I would call it 332 joules. Okay, 49 is next. This is very interesting. I think we've gone 10 minutes and my computer hasn't quit yet. 49. Okay, so I've got a 0.145 kilogram baseball.
Knock on wood.
Is dropped from a tree, so I need a tree. Okay, so there's a tree. 12 meters high above the ground. With what speed will it hit the ground, ignoring air resistance? Okay, so I got some potential energy, M, 0.145 kilograms, G, 9.8 meters per second squared, times H, 12 meters. 0.145 times 9.8 times 12. I have 17 joules. Now 17 joules is going to be changed to kinetic energy, so that 17 joules is 1/2 mass velocity squared. So V is going to be the square root of 2 times 17 divided by 0.145. Square root of 2 times 17 divided by 0.145. 15.3 meters per second. Okay, that's much easier than what we had to do in Chapter 5. I don't know if you noticed that or not, but
Yeah, I definitely did.
that's what it is. Alright, so that was 49. Oh, if it actually hits the ground at 8 meters per second, what is the average force? So this is my A answer. So my B answer says my kinetic energy was really 1/2 mass velocity squared, was really 8. 8. The velocity was really 8. So the velocity is really 8 meters per second. So now my kinetic energy is not the same as my potential energy. 0.145 kilograms times 8 squared. 8. Okay. 0.5 times 0.148 times 64. And I really had 4.64 joules in my kinetic energy, not the 17. So that being the case, if I take my potential energy minus my kinetic energy, I'll get the work done by friction in joules. And so I got 17 minus 4.64.
Wait, is it the 17 or the 4.64?
No, it's 17.
Oh.
The potential energy up here, right there.
Okay.
That we calculate right there, 17. Alright, so I got 12.36 is joules, is the work done by friction, and that's going to be force over a distance, and we want to find that force. So the force is going to be 12.36 joules divided by the 12 feet high that I am. I assume the tree is 12 feet high. Yes, it is 12 meters high. Alright, so I got that number divided by 12. I end up with 1.03 newtons as my force of friction that is being applied to slow me down. Alright, now we're looking for number 60. A car is generating 18 horsepower when traveling at 95 kilometers per hour. Kilometers per hour do me no good at all. I'm going to divide by 3.8 and come up with meters per second. 95 divided by 3.8, 3.6. We'll call it 26.39. 26.39 meters per second. All right, and we're working on 60. What must the average force exerted on the car due to friction and air resistance? Okay, so that entire 18 horsepower is being used to against friction. There's no friction, the car would still go 95 kilometers per hour with no problem. But you need the 18 horsepower to get down. So now we want to take 18 horsepower and change it to something that's useful. Alright, so we look in front of the book and we see that 1 horsepower is 746 watts. So 1 horsepower, 18 horsepower would be 18 times 746 watts per horsepower. Alright, so 18 times 7, 4, the other 4, 6. So I've got 1, 3, 4, 2, 8 watts. Now watts are in joules per second. Joules per second. So every second I'm dissipating 1, 3, 4, 2, 8 joules, which is going to be the work due to friction, and that's going to be force over a distance, and we're looking for that force. So the issue is, how far do we go in 1 second? Well, we go 26.39 meters in 1 second, so that's my distance. So the force due to friction, 13428 joules divided by 26.39 meters per second, and I end up with newtons as my final answer. 13.428 divided by 26.39, and I end up with how many significant digits do I'm looking for? I'm looking for 2, so I'm going to call it 820 newtons for my final answer. Okay, next guy is number 67. And 67 says a pump lifts 27 kilograms of water per minute through 3.5 meters. What is the minimum rating of the pump that I have to do? Okay, so I have some potential energy I need to get that high. Mass, 27 kilograms per minute times 9.8 meters per second squared times 3.5 meters is going to give me some joules per minute in my potential energy. But my potential energy really isn't joules per minute, it's really in joules. But we can go that way. 27 times 9.8 times 3.5 equals 926.1 joules per minute. Okay, and we're going to multiply that by 1 minute per 60 seconds. And we're going to divide, so we're going to divide by 60. Divide by 60. And we're going to want 15.435 watts because we have joules per second. So we want 15.435 watts, and it wants to know the minimum rating of the motor to do this. Well, if I have, looking in the front of the book again, 746 watts per horsepower, 1 horsepower, and I have 15. I have 15.435 watts. How many horsepower do I have? So horsepower 7. Okay, the horsepower goes on top over there, and that goes on the bottom over there. So I've got 15.43 whatever divided by 746. Change to a fraction. Alright, so I've got 0.0206 horsepower. Alright, now I can buy motors, right? Can I buy a fractional horsepower motor? Yes, I can. I can buy a quarter horsepower motor. That'd be 0.25 horsepower. Or I could get an eighth of a horsepower motor, 0.125 horsepower. And I can get a 16th of a horsepower motor, 0.600615. 0.6025 horsepower, but I can't go below a 16th of a horsepower motor, so I'm going to need a 16th of a horsepower motor to do that, to pump all of 28 kilograms. That's not a whole lot of water in a minute. And that ends problem set for chapter 6.